Now we are going to find the values of a2 and b2 using the same boundary conditions. Okay. So this is the second case, and we have found big X of x equals to a2 e to the ax plus b2 e to the negative ax, or if you want you can write the hyperbolic trig functions or use the hyperbolic trig functions to express the same solution set. Now I am going to consider this the first equation to find the values of a2 and b2. Okay. The first boundary condition says when x equals 0, your big X of x equals to 0. So now if you evaluate this one at x equals 0, you will get a2 e to the a times 0 plus b2 times e to the negative a times 0, and this summation equals to 0. Okay. So this is e to the 0, e to the 0 is 1. Basically we have a2 plus b2 equals to 0. It means a2 equals to minus b2. Okay. Next we are going to use the second boundary condition, and if you evaluate this equation at x equals pi, then it should be 0 as well. So now we get a2 e to the a pi plus b2 e to the negative a pi equals to 0. Okay. But the value of a2 equals to negative b2, so what we could do is we could express this equation in terms of b2 only. So we have minus b2 e to the a pi plus b2 e to the negative a pi equals to 0. Okay, let us factor out b2 from these two terms. Okay. Great. So now we have a product that equals to 0, but we know that these two, the sum of these two terms does not equal to 0. Therefore, the only possibility is that b2 must be 0. Okay. If b2 equals to 0, then a2, so this implies a2 equals to 0 as well. Okay. So this means our big X of x equals to 0 as well. 0 as well. So the next and the final case is this one. So in the final case we consider negative lambda values. Now we have was it negative lambda values? Let us see. Sorry, we consider positive lambda values. So lambda, we set lambda equals to a squared, and then we got big X of x equals to a3 times cosine ax plus b3 times sine ax. Okay, let us use the same boundary conditions and let us figure out the values of a3 and b3. Okay. So when x equals 0, you have a3 times cosine of a times 0 plus b3 times sine of a times 0, this equals to 0. Okay, so this is sine 0, sine 0 is 0, this term equals to 0, but this term equals to 1. So basically we have a3 times 1 equals to 0, therefore a3 equals to 0. Okay, now let us use the right boundary condition. So, now we need to evaluate this equation at x equals pi. So, at x equals pi, so now since a3 equals to 0, we do not get this first term and we do have only the second term. b3 times sine of a times pi, and this equals to 0. Okay. Now, remember, we are looking for non-trivial solutions. So, here I have a product again equals to 0. So, if you set b3 equals to 0, then this entire function becomes 0 and you will get a trivial solution. Now, since we are looking for non-trivial solutions, now let us say b3 does not equals to 0, because we have a product that equals to 0. It means either b3 can be 0 or this sine of a pi term can be 0. If b3 does not equals to 0, then the only possibility is that sine of a pi must be 0. Now, as you know, sine of an angle becomes 0 when you have an integer multiple of pi, when your angle equals to an integer multiple of pi. So, if I write it down, then this angle should be an integer multiple of pi. So, here n is an integer, n goes from 1, 2, 3 up to infinity. Okay. So, this says if a equals to n, if a is an integer, then we can satisfy this equation and even the boundary condition. Okay, so let us update our big X of x. So, now big X of x equals to a3 is 0, but now we have b3 times sine of, instead of a, now I can write n, nx. nx. Great. And let us make a quick note, and we set lambda equals to a squared, but a equals to n, therefore lambda equals to n squared. Okay. Great. So, now we do have a non-trivial solution for the function big X of x. So, the next step is to solve the ordinary differential equation that we obtained for big T of t.